This is part 2 of the series Relationships Within Triangles, and we're going to start off this part with a discussion of points of concurrency. Now, a point of concurrency, as you can see here, is the point of intersection of three or more lines, razor segments. In this case, it's going to be lines, razor segments in triangles or relating to triangles. The first point of concurrency we're going to talk about is called the circumcenter. And the circumcenter is the point of concurrency of the perpendicular bisectors of the sides of a triangle. We've already talked about what perpendicular bisectors are. So point D is the circumcenter, the point of concurrency, the point where all three perpendicular bisectors of the triangle sides coincide or are concurrent. And the current circumcenter theorem states the circumcenter of a triangle is equidistant from the vertices of the triangle. And this is a very interesting one. And the reason it's interesting is because if you actually find the circumcenter, what it's telling you is that circumcenter is the center of a circle that will go through each of the three vertices. So no matter where the vertices are, that point will be the center of a circle where these 3 points are on the circle someplace. Now, in some of these points of concurrency, we're going to see that the point of concurrency was within the circle. In this case, with the circumcenter, that's not necessary. Here, in triangle ABC, point D is the circumcenter. That means that ED, DF, and DG are perpendicular bisectors, and DA, DB, and DC are equidistant. And you can tell that because here is a circle with point D as its center, and AD, DB, and DC are radii. Now if I move point A around, you can see that if I move it in a certain place, A, B, and C are still on the circle, but the circumcenter is outside the circle. And I can do that in any of the 3 dimensions. I can move it from top to bottom, left to right. Either way, I can make that circumcenter go wherever I want it. But the critical point is that circumcenter always goes through the 3 vertices of the triangle, making each one of these segments from the circumcenter to the vertex a radius, and therefore all congruent. So let's go ahead and work an example using circumcenter and see if we can get these concepts in our head. So here we're given triangle ABC, and these are our coordinates. We're looking for the circumcenter, so we need to find the perpendicular bisectors of each one of the sides of this triangle. Well, they made that fairly easy for us because, first of all, AB is a vertical segment and it's 4 units long. So you can clearly see that the perpendicular bisector, the midpoint, is going to be right there at 1. Remembering that midpoint is the average of the endpoints. 3 plus negative 1 is 2. 2 divided by 2, 1. So there's our midpoint. And the perpendicular bisector, the line that's perpendicular to a vertical line, is horizontal. So if we put in a horizontal line here, it'll look like that. Now we do the same thing with the bottom segment. So our bottom segment is 6 units long. Clearly half of that is 3. And a vertical line is perpendicular to a horizontal line. So if we put a vertical line in here, and we can see that they intersect right there at the point 3, 1. And if we want to actually go through and determine explicitly that that is in fact the midpoint of segment AC, that's all we have to do is calculate the midpoint of AC. And so the midpoint is the average of the endpoints. So we have 0 plus 6 divided by 2 and 3 plus negative 1 divided by 2 That gives us 6 divided by 2 is 3, and 3 minus 1 is 2. 2 divided by 2 is 1. So yes, in fact, that is the intersection point right there, and that is our circumcenter. So our circumcenter is at 3, 1. Okay, let's move on to the next section and see what we can find out there. In this section, we encounter our next point of concurrency, and that's called the incenter. And an incenter is the point of concurrency of the angle bisectors of the triangle. So circumcenter was perpendicular bisectors. Now we have angle bisectors. So AD, BD, and DC are angle bisectors. And the incenter has the distinction of being equidistant from the sides of the triangle. So as you remember from our angle bisector theorem, any point on an angle bisector is equidistant from the sides of the angle. Well, if you just eliminate these two vertices, you can see that angle FAG is an angle, and if AD bisects FAG, then clearly that point must be equidistant from this side as it is from this side, making FD congruent to DG. When we throw in the rest of the triangle, this has to be equidistant to this, and if this is congruent to this, all three of these have to be congruent. So that's where this theorem comes from. The name incenter is a convenient name because an additional feature of incenters is they are always inside the triangle. So let me show you another dynamic picture here, and we can see that in action. So here we have another triangle, and AD, DB, and DC are all angle bisectors. So that makes D the incenter. Now if I grab one of these vertices and start moving it around, you'll see that no matter where I put it, the incenter, point D, is always inside of the triangle. Always inside. So very important artifact there. And the fact that these three sides, FD, DE, and DG, are all going to be congruent is what we're going to be using to solve our various problems. So let's go ahead and work a couple of examples using incenter and go from there. Now before we try to solve anything with this problem, let's first analyze what we have here without regard to any of the text that's given to us. Let's see if what we can figure out. Well, I can see that NC is cutting angle ECF into two equal pieces, and AN is cutting angle DAG into two equal pieces, and BN is cutting EBD into two equal pieces. So clearly these three segments are angle bisectors, making point N the incenter, which means NF, ND, and NE have to be equal. Now the tip-off there was the fact that this segment is perpendicular to the side, and we know that the distance from a line to a point not on the line is the length of the perpendicular segment from the point to the line. So this clearly tells us that those three are the lengths, the distances from that point to the sides of the triangle. So now let's go ahead and assimilate the information they give us and see what we're trying to figure out here. They first give us an expression for ND, the length of segment ND, which is this piece here. And they say NE is equal to this expression. Well, because this is the incenter, ND and NE are going to be the same. So when we find the length of ND, we will have the length of NE, and we will also have the length of NF, which is what we're trying to find in the first place. So let's go ahead and find that value. So knowing again that ND, this piece, and NE, this piece, are exactly the same because that's the incenter, we'll use that to form an equation. So 5x minus 1 equals 2x plus 11. Let's subtract our 2x. 3x minus 1 equals 11. Add the 1. 3 equals 12. Divide by 3. X equals 4. And now we're looking for any one of these segments. So let's put it into ND. That'll give us the easiest one. So 5 times 4 minus 1 is 20 minus 1, 19. And so because ND equals 19, so does NE, and so does NF. So that's our answer for part A. Now part B says, can NG be equal to 18? Explain your reasoning. To work this one out, I'm going to redraw triangle NFG here. Just going to make a really grotesque, rough example here. And so this is F, this is G, and this is N. Now they're saying, can this be 18? Well, we just found out that NF is 19. And you know, in a right triangle, the longest side is the hypotenuse of the right triangle. And so this side can't be less than this side in order for this to be a right triangle. So the answer would be no, this can never be 18 because it has to be greater than this distance. And not only that, the shortest distance between a point and a line is the perpendicular distance from the point to the line. And since NF represents the perpendicular distance, this cannot be shorter than this, because this has to be the shortest distance from that point to this line. So any way you want to answer it, the answer is no. It can't be 18. So let's move on to the next problem. In this problem, we have another incenter because we can see QL and QK are angle bisectors. These all represent the distances from that point to the side, and therefore point Q is the incenter. And that means that QN, QM, and QP are all going to be congruent. That means they have the same length. So QM is going to be equal to QN. And so we're looking for QP. So again, just like in the last problem, let's just set these equal to each other, solve for x, and substitute. So we have 3x plus 8 equals 7x plus 2. Subtract our 3x. 8 equals 4x plus 2. Subtract the 2. 6 equals 4x. Divide by 4. 6 over 4 equals x, which is 3/2 equals x. Let's take that value, put it into here, and we'll have 3 times 3/2 plus 8. That's going to give us QM, which is going to be the same as this. So that's 9/2 plus 16/2, which is 25/2, which is the same as 12.5. Okay, well that takes care of incenter. Now let's move on to the next section.